G'day team, welcome back to another video on linear programming, and today we're going to look at multiple optimal solutions. Now in the last video we looked at using our simplex and then using the vertices to substitute into our objective function to find either our maximum or minimum solutions. Now we're going to look at what happens when we actually get multiple optimal solutions and the process we need to take to ensure that we're accounting for every single multiple solution or optimal solution that we can have in a question. So hopefully you've had a bit of a chance to read this question here, and I've gone ahead and created our table to allow us to then do our constraints. So we've got a store that sell gift baskets. They've got small baskets and they've got large baskets, and they've got a certain amount of chocolates, balloons, or roses in each of the baskets, and it gives us limitations. Now, it tells us that the small baskets sell for $20 and the large baskets sell for 40. So that is what we are going to maximize, okay? Now, what you can do to check if you've got the right order, I always like to put these limits and have the limits in there, and that kind of indicates what must go in chocolate, like in these sort of columns here, and it makes it a bit easier to then distinguish what x and y are going to be. So our objective function for this problem is going to be 20x plus 40y, and that is what we are going to try and maximize. Now, what you can do to make it easier is obviously take out a factor of 10, and it still will give you the right answer, but we're going to leave it in 20x plus 40y form. Now, for our constraints, we're going to have 5 constraints in this question. Now, because we are dealing with real things, we can't have negative amounts of small basket and large baskets. So that means we must have x is greater than or equal to 0 and y is greater than or equal to 0. And what this does, that just accounts for any issues we get with negative x's and y's. The next thing we're going to use is our columns here. So we're going to have a constraint for chocolates, for balloons, and for roses. And all you are doing is correlating the column to the variable. So I've got 5 lots of x's, 10 lots of y's, and 80 is my constraint. Now I've only got 80 chocolates. So that means if I have 5 lots of x plus 10 lots of y has to be less than or equal to 80. So that's going to be my first constraint. My second constraint is the balloons, which is just going to be x plus 6y, and I've only got 36 balloons, less than or equal to 36. And then finally the same with roses, so 12x plus 12y is less than or equal to 168. Now that we have our constraints, we need to graph. And you'll see down below, I've created an axis already. And you'll see it's got some numbers there, but we don't really know where to put our equations. What's going to be the easiest thing to do is to put our equations onto your graphics calculator and solve for the x and y intercepts and draw our line through. Now, you've got to be careful if we use our graph function in our calculator, it only accepts y equals equations. So we need to rearrange our equation for y, so our constraint for y. Now y is here, so I'm going to subtract 5x, and then I'm going to divide everything by 10. So y is going to be by itself. I've got 80, take 5x, and then divide everything by 10. So I'm subtracting, the 5x and putting the coefficient of y on the bottom. So if you use that same logic, I've got y less than or equal to 36 minus the x term divided by the coefficient of y. And then finally, y less than or equal to 168, take 12x all over, and then I've got 12. Now, obviously, a lot of you can see some simplifications that are possible in some of these equations, but to make things a bit more efficient, if you can't see them straight away, you can use this type of rearranging an equation. Your calculator will automatically sort of fit it to what we would like it to do. Now, if we are looking at our first equation, the y equals 80 take 5x over 10, that has an x coordinate of 16 and a y coordinate of 8. Now you can check that on your own, but just save time. So 16 and 8, and we draw a line between them. and make sure that you are then labeling your equation. So this is my y is equal to 80 take 5x all over 10. Okay, that's my first equation. My second equation I'll do in blue has an x-intercept of 36 all the way over here and a y-intercept of 6, which is just here. Draw it right across, and then we're going to label that guy as well, which is y equals 36 take x all over 6. And then we've got one more equation I'll do in pink, which is the final one, which has an x and a y-intercept of 14. So 14, draw that nice and straight through. Lucky my iPad does it for me. And we get our equation. Take 12x all over 12. Now, given these are all less thans, we need to shade the region that is going to be less than all of those. And as you've probably figured out by doing a lot of these questions by now, it is this region under here. So we're going to give that a quick highlight through just to make it super obvious. Just a nice quick one just so you can see. And we know from the last video that our vertices of that region, our corners, are where our optimal solution lies. So I've got here, 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 and here. So in this case, I've got 5 different vertices I need to check. So we move down and we write those coordinates in. So I've got the origin 0, 0. I have the y-intercept 0, 6. I have the x-intercept 14 and 0. And I have these 2 intersection points. Now, I've drawn my graph nicely that I can find those values. If you've drawn yours a little bit weirdly, different scales, not quite as accurate as a technological piece can do, then I would suggest using your graphics calculator and find the intersection using your GSolve. But we've got 2 intersection points, and they are 6 and 5 and 12 and 2. Now, if we substitute these x and y values into our objective function that we had earlier, we get the following results. We get 0, we get 240, 260, 320, and 320. Now, what we did last time was go, whoop, we've got one maximum number there, that is our optimal solution. But you can see that both of these vertices give the same maximum. Now, if I relate those 2 points, 6 and 5 and 12 and 2, onto my graph, I get, I'll do it in orange, this point here and this point here. And we can see that they are joined by this orange or red line segment, okay? Now, that line segment is super important because every coordinate that is a whole integer number is an optimal solution along that line. So we need to find if there are any other integer solutions between 6 and 5 and 12 and 2. Now, the easiest way to do this is to look at the difference between x values and the difference between y values. So we can see that from 6 to 12 in our x is 6 numbers different. From 5 to 2, sorry, I've undone my bracket, there's only 3. So it's going to be much easier to check our y values. So if I go a blank and then a 3, a blank and then a 4, we can actually see that there's only 2 coordinates that we need to check. So we need to ensure that along this red line, that the coordinate that has a y of 3 is also an integer, and the x coordinate with a y of 4 is also an integer. So again, we can do this in our calculator. We can go xcalc and throw in our values. All I'm going to do is show you quickly on Desmos. All right, so we've got our red equation here that we're looking at. Pretty sure that's right. Yep, so 6 and 5, 12 and 2, it's our red one. If we look through here, if we're looking at our y coordinate, if I look at the 4 and go across to the red, we can see that correlates to 8. And if I've got 3, that correlates to 10. So, as we can see, all 4 of these coordinates are integer points and lie on our line segment between our 2 maximum vertices. All right. Now, if you are checking the x's like we just were, you could use yCalc, but if we're checking the y's because they're a smaller gap, we can use xCalc. All right. Hope this helps, and we'll see you in the next video.